Hello guys, welcome back to Chemistry Digest. If you are new to this channel, please make sure you hit the subscribe button and also turn on the notification bell so when I post videos like this, you'll be the first to get notified. Alright, let's discuss the electronic configuration of ions. In the previous video, we learned how to write the electronic configuration of neutral atoms using the orbital notation. Today, we'll be using the same notation to write the electronic configuration of ions. Before we start, let's define ions. Ions are simply atoms or group of atoms with an electric charge. These charges might be positive or negative. The positively charged ions are known as the cations, while the negatively charged ions are called the anions. Here are some ions you may be familiar with. For the cations, we have the sodium ion, magnesium ion, and aluminum ion. And for the anions, we have the fluoride ion, the chloride ion, and the oxide ion. The positive ions or cations are formed when atoms, mostly metallic elements, lose electrons, while the negative ions or anions are formed when non-metallic elements gain electrons. So let's look at some rules applied by writing electronic configuration of ions. For cations, which are positive ions, they are going to be formed by the loss of electrons. So at the end, we are going to subtract the electrons from the outermost shell. So basically what we're going to be doing is to subtract electrons from positively charged ions to arrive at their electronic configuration for cations. Then for anions, we are going to add electrons to negatively charged ions to arrive at their final electronic configuration. Alright, bear that in mind as we start with cations, which are the positive ions. So let's deduce the electronic configuration of sodium ion. Now for sodium ion, being a cation, it is going to lose an electron which is equivalent to the magnitude of its charge. So what's the magnitude of the charge of sodium ion? It is +1, alright? So it's going to lose one electron from the outermost shell, which is the 3s orbital. So after losing an electron, it becomes 1s2, 2s2, 2p6. Now this electronic configuration now looks like the electronic configuration of neon, which is a noble gas, or you call it a rare gas or inert gas. Alright, this is a JAMB question, mind you. So this electronic configuration of 1s2, 2s2, 2p6 has achieved octet stability and is now having 8 electrons in the outermost shell. I hope that is simple. So for magnesium ion, which is also a cation, it's going to lose the equivalent of the magnitude of its charge. In this case, it is +2. So it's going to lose 2 electrons from the outermost shell, making it 1s2, 2s2, 2p6, also looking like the electronic configuration of a noble gas, which is neon, also attaining octet stability. Alright, let's move on to the electronic configuration of anions, which are negatively charged ions. Okay, anions are formed by gain of electrons, alright? So electrons are added to the valence shell. The valence shell simply means the outermost shell, the shell that contains the valence electrons. So you can see valence electrons are outermost shell electrons. They are the ones that take part in chemical reactions, alright? So let's consider chloride ion and sulfide ion. So looking at the chlorine atom, which has 17 electrons and whose electronic configuration is 1s2, 2s2, 2p6, 3s2, and 3p5, it is going to gain 1 electron. Remember, anions are formed by the gain of electron. So the number of electrons it will gain is determined by the magnitude of the charge, which in this case is 1. So at the end of the day, 1 electron is added to the outermost 3p5 shell to become 3p6. That is from 3p5 to 3p6. And altogether, we are going to have 1s2, 2s2, 2p6, 3s2, 3p6. Just like you guessed, it has achieved octet stability, and now it looks like argon when it comes to electronic configuration. Beautiful. So for sulfide ion, the magnitude of charge is 2. So to form the electronic configuration from sulfur atom, it is going to gain 2 additional electrons to transition from 3p4 in the outermost shell to 3p6. And altogether, we have 1s2, 2s2, 2p6, 3s2, and 3p6. Also similar to chloride ion and argon's electronic configuration. You can see how they are now related. So let's look at a special case here, which is the electronic configuration of transition metals. So for transition metals, electrons are removed from the highest principal energy, and we have that 3d is higher in energy than 4s. If we go by that rule, we will have that the electrons are supposed to be removed from the 3d orbitals before removing from 4s orbitals. But something happens in this situation. 4s orbital becomes slightly higher in energy than 3d orbital during electron filling, and thus, going by the rule, electrons will now be lost first, starting from the orbital with the highest energy. So the narrative changes as 4s orbital is now slightly higher, so electrons will be removed first from the 4s orbital. So in all, memorize this phrase: if it is filled first, it is removed first. Hence, we remove electrons from the 4s orbital before removing from the 3d orbital. Now, let's put that into practice. Let us start with the electronic configuration of ion 2 ion. Ion is going to lose 2 electrons first from 4s orbital to become 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. You can also have it in this form that combines the electronic configuration of argon with the remaining 3d orbital. It is just like the shorthand method of writing the electronic configuration of transition metals using argon as the benchmark. So for ion 3 ion, the same method is applied as 3 electrons are removed. 2 is removed first from the 4s orbital, as it is the much that can be removed from s orbital. Then the remaining 1 electron is now removed from 3d6 to become 3d5. So altogether we have 1s2, 2s2, 2p6, 3s2, 3p6 and 3d5, or just like we did before using the argon notation. We'll end this segment by solving some questions. Make sure you drop your answers in the comment section. Until then, see you next time.